IoT Unplugged. Tune in to the Internet of Things. You've heard of machine learning, but what about federated learning? Although less well known, the process can provide IoT devices with real tangible benefits: security, lower latency, and model robustness. By allowing devices to learn from their collective data without sharing sensitive information, it could prove critical for wider adoption of IoT as a whole, and also get AI on board easier. Yet, as mentioned above, the concept is not as widely deployed. But why not? And what are the hurdles to its implementation? To discuss this, I'm joined by Eric Topham, co-founder and CEO of OctaiPipe. To discuss this, I'm joined by Eric Topham, co-founder and CEO of OctaiPipe. Thanks for joining us today. If you could just start by introducing yourself and what OctaiPipe does.
Yeah, thanks very much, Christian. Yeah, great to be here, and thank you for having me. So, my name's Eric Topham. I'm the CEO and one of three co-founders of OctaiPipe. So, my background is that I was in academia, did my PhD, came out, worked for a few years in public health and healthcare research as a data scientist before setting up a business which at the time was known as TDAB.ai, that has since evolved into what we are today, which is OctaiPipe. So OctaiPipe is a federated edge AI for IoT platform. Now that sounds pretty jargonistic, so I'll break it down a little bit. In essence, we are a platform that allows scientists, data scientists, and engineers to build, deploy, train, and then manage in production machine learning algorithms in highly distributed IoT systems, but in a way that is incredibly privacy and security, so privacy preserving and security enhancing, and has the added benefit of being extremely efficient in terms of network and cloud compute resources. So really what we are about is solving a set of challenges that happen when we try to develop machine learning for the purposes of AI at scale in IoT systems. So IoT systems are complex. They exist in the physical world and they are subject to the effects of the physical world. And this means that basically there's a lot of scarcity of the important events that we often want to train our machine learning to predict. And we have a lot of what we call heterogeneity, so difference or diversity in that data. And so this means that in order to learn for a problem well, we actually need to learn at a very large scale in order to kind of experience the world in a representative way. If an algorithm only sees a sort of small subset of data, it doesn't sort of accurately represent the world. And so when we then take that algorithm and try and deploy it to do whatever intelligent task it might be in the real world, then it just doesn't translate properly. So we need to get to real world scale. The problem is when you try to get to real world scale, you run into a couple of kind of core fundamental challenges. One is a challenge of risk, and the other is a challenge of cost. And so what I mean by this is that as we try and move large volumes of data from IoT devices over the networks on which they're connected and up into a central cloud, we expose them to various points of risk in the system in terms of cybersecurity risk, and indeed, of course, perhaps of governance risk, ownership risk, or even security and defense risk, particularly where these systems are operating where the devices that we're dealing with are perhaps owned by different parties, or indeed different parties from the entity that's trying to create the algorithm. So these kind of privacy, security issues become very, very important. And so we care about this in systems where, like I say, we have critical infrastructure where if people get hold of data or get hold of algorithms and do bad things happen. So like I said, that could be to do with personal data privacy, it could be to do with defense and security, could be to do with an element of IP and ownership around the data. Second part is that, of course, as you scale these systems, what is a small amount of data that comes from one device over a network, when we get to real world scales in IoT where we've got tens of thousands, hundreds of thousands, even millions of devices, the cost of the movement of what is, if an individual device, a small amount of data over a network and up into the cloud suddenly becomes pretty vast. and it's just uneconomical in many cases. In fact, the cost of training the algorithm when we've had to move all of this data in this way, it means that the benefit is outweighed by the cost of getting there. And people have dormant use cases that they don't actually try and solve because it would just cost them too much to do so. So that's basically what we solve through this technology called Federated Learning, which allows us to train on the device without having to move all of that data over the network up to the cloud. That keeps the data private, and it means that we have very, very low costs on the network in the cloud environment.
Okay, so let's move on to federated learning. You've given us an overview about what OctaiPipe does, and you're talking about federated learning. So, in a layman's term, in comparison to machine learning, what is federated learning?
Well, federated learning is a form of machine learning. It's just that how do we get to the end result that's a little bit different. So in machine learning, what we're doing is learning a set of relationships between effectively a set of inputs and some desired output that we wish to estimate. And fundamentally, what we're doing from a mathematical and statistical point of view is learning a set of distributions and the correlations between them. So in sort of the normal machine learning that everyone is familiar with, what we do is that we build a single, what we call concatenated or kind of joined up data set on which we then compute a set of model parameters to basically learn this relationship. And so when we do this traditionally in the IoT world, what we have to do is take the data from the devices that are out there in the real world, collecting all this data from these sensors, and then shift it over the network and up into the cloud, put it all in the database, and then compute these model parameters to learn whatever relationship it is we're interested in learning. Well, in federated learning, what we do is the opposite. We kind of completely flip the whole thing on its head, and we say, well, instead of moving all of that data onto the cloud, why don't we move the learning model down to each of the devices from which we want to learn, and then let's learn a set of model parameters per device that's in our population. And so we learn one set of model parameters per device. If, for instance, I have 100 devices in my population, I learn 100 different sets of these model parameters on the data at the device level locally. And then what we do is we send in a message packet the values of these model parameters back over the network up to a central node of aggregation where we have an aggregation algorithm that aggregates the contributions from each of the individual devices in our population from which we're learning. And once we've got this aggregated model, what we call the global model, this global model basically has the same parameter values as we would have obtained if we'd moved all of this data up to the cloud and put it in a single data store. But the magic trick is that we never moved any of the original raw telemetry data, and all we moved was a few kilobytes of information in the message packets to this node of aggregation, and the global model gives us the same performance. And then once we've got the global model, then we can do what we want with it. We can deploy it back to our edge devices where it can then go and do whatever intelligent task we've designed it to do. So again, the benefits really are that because the data stays on the local devices, it's incredibly privacy preserving to the device. And secondarily, it means that the network loads and the communication overheads and the cloud computation overheads are hugely reduced. And to try and quantify that for people, if you consider 1 million solar panel systems on homes sampling the energy data at a 1-minute interval, the difference in communication overhead between federated learning and moving that same data to the cloud for the purposes of doing forecasting is about a 50-fold reduction in favour of federated learning. And that difference increases exponentially as you increase the sampling frequency. So for very high frequency data, that benefit is exponentially greater.
Okay, can you give an example of an industry utilising IoT where the devices are on this federated learning model?
Yeah, for sure. So I mean, the wonderful thing about federated learning is you can use it almost anywhere. But I'll go back to the little example I was kind of tentatively giving there, which is so in the energy industry, in solar, we often have, in fact, the majority, I believe, of solar panel deployments are actually on buildings in which the consumer lives. And in fact, these solar green energy companies are trying to incentivize their customers to come to them by effectively offering them discounts, by helping them make decisions about whether to store, use, or sell back to the grid the energy that they're generating from the solar panels on their houses. Now, the issue is that you need that consumer data to build the forecasting algorithms that you need to predict the demand to then be able to make these kind of estimations of pricing and demand. But the challenge is that this energy data is actually quite sensitive because, of course, you can tell quite a lot about what's going on in someone's home from the patterns of energy demand. So therefore, not only is energy infrastructure critical in the sense that, of course, if malicious actors do something bad to their infrastructure, bad things happen, but also there is a regulatory risk, particularly in, say, the European and North American markets, around the personal data privacy and the preservation of that personal data privacy for the consumer. And indeed, the CTOs in these businesses are future-proofing themselves against the idea that the consumer will ultimately refuse to share data back to the energy company, and yet it's important for the energy company to give this high level of service to the consumer. So the solution here is to use federated learning, where instead of having to take that data from the consumer up to the cloud, where it's centrally processed by the energy company, instead we can ship the learning process down to the consumer's phone via the app that they run for their smart home energy, or down onto the smart meter as well. And we can train a local forecasting model in each home, and then simply move the model parameters back centrally to the energy company for the aggregation to build a better model. And then that better global model can then be shipped back to each consumer, where it can then do what it's designed to do, which is forecast their energy demand on an hourly basis. And that can then drive functionality in the app to recommend to them whether they should be making buying or selling decisions around their energy.
Okay, I was wondering maybe if you could tell me, as sort of only like the update of the model is sent rather than the full information. Obviously, there's some security benefits to this, but is there any sort of nuance lost by sending a condensed version of the information?
Well, no, in the sense that, if I move all of that data up to the cloud, it's still the same data that I'm with the same inputs and the same output that I'm estimating. It is true that perhaps there are, in certain contexts, that it may be more difficult to join data sets together if they're not locally, joinable, if that makes sense. So there can be some challenges there potentially. But in general, for the use cases that we're seeing people trying to solve, there isn't a loss of information. It's not because we have aggregation that there's a particular level of information loss. Now, that said, there is a challenge in IoT, which is, as I said right at the beginning, we have these kind of very heterogeneous systems. And so, for instance, if we think about like something that looks like the normal distribution, well, in IoT, a simple case is that we might have something like a very skewed distribution where you have a bunch of devices that are in the long tail. And so, if you like, the global model may work very well for models that are for devices that are in the kind of the central bell of the distribution, but not so well for those that are in the long tail. But actually what we can do with OctaiPipe is not only can you generate this global model, but when you deploy it to your devices again, you can allow it to do a fine-tuning step, which basically sort of relocalizes the model one final time to the device. And so what this does is that for those devices that are in the long tail of the distribution, they kind of relocalize the model. So they've got something that's more customized to them than the global model is. And so when we look at the evaluation of the performance of the system overall, then that gives us a very nice performance uplift. So it's a way of dealing with that heterogeneity.
Okay, moving on from the security benefits that federated learning brings, and what other benefits can it bring to IoT devices that people deploying it would deem it like an attractive machine learning method?
Yeah, well, actually, going back to your previous question around performance, one of the advantages is performance, because the typical way of doing machine learning in IoT systems generally with edge deployments, or indeed perhaps even more specifically in the world of tiny ML, is generally that people train models in a one-to-one relationship with the device, which basically means that the model is very specific to that device, which is a problem because when that physical device, which exists in the physical world, then encounters a set of conditions that were not encountered when the model was originally trained, then the model does badly. It's what we might call overfitting. Now, the nice thing about federated learning is that you can train across a large number of devices at very, very low cost in parallel, which not only speeds up the rate of learning, but effectively means that you learn on a wider representation of the world. And so even if not every individual device experiences every possible set of conditions, across that population of devices, you will cover a broader range of potential conditions and states. And so that means that the global model will effectively kind of incorporate all of that learning. So an individual device then benefits from the learning across a whole population. And so actually we get better performance using federated learning often than both the one-to-one learning, or indeed if we centrally learn as well. We've got good benchmark proof that you can outperform putting data up into a central database. And then with this fine-tuning step, then it actually gives you another performance uplift. So we got some really nice work from wind turbines that show that you get about twice as good performance in federated learning in these kind of sparse and heterogeneous data sets than you do by trying to ingest data to the cloud. And then if you allow this kind of customization of the global model to the individual device after you've done the federation process, then you get a sort of about 10% improvement. Again, so performance is a big advantage. We've mentioned privacy preservation, but like I said, the costs of learning are vastly reduced. And that's because basically your network cost and your cloud costs stay almost fixed. So as you add nodes into the network of devices from which you want to learn, the only thing that increases from the network and cloud perspective is a small increase in total load on the network as you add more message packets. But basically your cloud or centralized aggregation cost, the server there, is just a fixed cost. And so as you grow that network, you learn on larger and larger networks, your cost remains fixed. Whereas in the cloud, if you move everything to cloud over the network, basically you have an exponential increase as you add devices and you add sampling frequency.
Okay, moving on to the next question. I think we've covered quite a couple of questions in that answer. So you might have covered this, but let's bring it in again. What challenges or limitations does federated learning present in the context of IoT? And is there any sort of mitigation tactics that can be used?
Yeah, absolutely. So there's a whole host of things we could talk about. And the first thing to say is where there are challenges, I think there's real opportunity as well. So one thing that is interesting is that in federated learning, of course, we're doing things in a very sort of distributed way. We often want to learn in a kind of autonomous manner. And there is one data type that is a little bit trickier to deal with, which is images in computer vision. So if we consider that there are kind of three broad data types, we have text, we have time series, signal data, and we have images. These kind of three broad things we have in IoT. Well, text data is sequential, a sequence of words is correlated to a following sequence of words. So this is something that's quite easy to train autonomously on a device. And indeed, next word prediction was one of the original applications of federated learning. So the thing that powers your predictive keyboard, those were originally trained using federated learning on phones. Time series signal data, similar story. We have correlation within a single time series, autocorrelation, one time step to the next. Or indeed, we can also have correlation between two time series. So we can train algorithms on a single time series or between two time series. The third problem is images. And now the challenge with images is that image is the thing that determines that, if I were to hold up my phone to you on video here, the thing that determines that my phone is a thing called a phone is that we decided that this thing was called a phone. So the label is assigned by a human. And so ultimately, in image-based problems, computer vision, there needs to be ground truth validation of the labels by a human being at some point. Now, in some situations, federated learning can work well because we have perhaps a phone that a human is using, and knowingly or otherwise, they have an interface through which they can validate labels. But in more autonomous systems that rely on computer vision, this is obviously more of a challenge if we don't have a human there and we're trying to learn new labels. So that's more challenging. The other big challenges in sort of federated learning for IoT really come from the nature of IoT systems. So the fact that we have very large scale, we have intermittent and variable connectivity, degrees of bandwidth, compute availability on the edge devices, heterogeneity of device specs, which can do things like affect the rate of learning on individual devices. And indeed, the fact that, like I said, the data that's generated in IoT systems tends to be quite heterogeneous. It doesn't follow necessarily sort of nice, clean, normal distribution. So all of these things present challenges. Now, there are lots of mitigations. I'll use one as an example. So in normal federated learning that we might find, like vanilla federated learning we might find in, say, healthcare research, where perhaps we want to learn a model across 10 hospitals. These 10 hospitals have a local server each. It's constantly powered, it's constantly connected via Ethernet to the network. And so normal federated learning, what we do is called synchronous updating, where basically we wait for all 10 hospitals to have a set of model parameters ready before we then upload those over the network for aggregation. Now, this is fine in our 10 hospitals where we're constantly powered, constantly connected. But if we compare that to a situation where we have maybe even only 1,000 mobile phones that have, different degrees of quality of network connectivity, where perhaps phones, some are running out of battery or have run out of battery and are off, where people are driving through black spots, out of 1,000, there's a very high chance that at least one of those isn't going to be available to do our synchronous update. And so if we then expand that out to real world scale, you can see how we could get very easily log jammed in a system like that. And so in IoT with federated learning, we have to do some, we have to design things differently. So for instance, one of the things that we do is do asynchronous parameter updating, where devices can contribute to the aggregation as and when they are ready. But that in turn can lead to problems where perhaps some devices are contributing more than others. So we have to have other strategies in place to make sure that we can recognize which devices are contributing so that they don't over-contribute. We stop them from contributing if they've already contributed a certain amount. So with OctaiPipe, when we talk about being a specialist platform for federated learning in IoT, it's these innovations that we are really specialist in leading on, in solving, so that FL delivers best-in-class performance and best-in-class scalability.
Okay, I want to move on to power, and that is power within IoT devices. I was wondering, do these computations that are being done closer to the edge, will that have an adverse effect on the lifespan of these IoT devices? And if so, how can things be mitigated? I know less data is sent via federated learning, but is there any concern regarding that?
Yeah, of course. So it's a very good point. So there is a trend, I think, in the IoT market towards, sort of battery-powered devices, and these batteries need to have a certain lifespan. It's not necessarily going to be possible to go and change, those batteries if they run out. So this is a challenge because while the amount, the load on the network and is less and therefore requires less energy because of these very small message packets that we're sending. What remains is the fact that we need energy in order to power the computation of our model parameters during both learning but also during inference. Now, in the world of tiny ML, it's well known that one of the things we need to optimize for is, in a sense, not just the accuracy of the algorithm, but the amount of energy that it uses in computing the prediction. And in fact, when we design these systems, it's necessary to actually sort of find a good trade-off between power consumption often and accuracy. And so we have to have the same consideration when it comes to training. So if on the one hand, we've got sort of deeper neural networks with more parameters in them, it's going to consume more energy to compute those parameters during training than it is perhaps for a decision tree based machine learning algorithm. And in turn, that may even be more efficient than perhaps a more simple class of linear model like a support vector machine. And so there are these considerations, and at the moment there are sort of a variety of solutions about how we get around this. So one thing might be to try and do training on a power device and deploy for inference to the battery powered device if that's possible. If we need to train on the battery powered device, then there are design choices by the user to be made about the type of algorithm that they're going to try and learn with, so that that they're not drawing too much power while doing the training. There's also an issue of how frequently we do the training. That's going to impact the power consumption as well. And the final point is also just about the what we actually run software-wise on the device. So one thing that OctaiPipe does is that try to be very, very lean, not just in the resource that's required from the containers that get deployed to the devices, but also in trying to be efficient in making sure that once we've obtained our train model, we tear down the resources that are on the device and then deploy a much leaner set of resources when we want to do inference, for instance. So yeah, absolutely, there are some considerations around it. And ultimately, where we're heading as a business is to lead the innovation into what people are starting to think of as tiny FL, which is following on from the world of tiny ML, which is mostly concerned with optimization of neural architecture for very efficient inference and perhaps single layer training. So to try and follow that on with innovations around how we can be much more computationally efficient for the training of neural networks, which obviously uses less memory and in turn has a benefit of drawing less energy. But we're probably a couple of years away from something mature there.
Okay, starting to wrap up now, but I have a couple more questions I'd like to ask you, and that is about sort of AI and its introduction to introduction to IoT. And I was wondering what kind of position do you think federated learning will play in IoT as AI's integration into it seems to expand and increase?
Well, I think it's obviously I would say this, but I think it's critical. In fact, I think it's a keystone technology, and it's going to be a catalyzer. So currently, I think the state of the world is that IoT systems are too complex. We've seen customers that have had dormant use cases simply because the systems are too user unfriendly to use to a degree. And then the next point is that the cloud-based infrastructures are very expensive and cumbersome to build. And so, economically, this is restrictive. And then there's the whole risk side of things. So we've seen customers, OEMs, for instance, of machinery that would like to build machine learning algorithms into their products, but can't because the data they need from from those devices is effectively sat and being generated with a customer who doesn't want to share it to them. So the distributed nature of IoT itself is effectively a barrier. And so we need to, if you're going to build these systems at scale, I think really the currency is trust, right? Like you need to be able to trust these systems. You need to trust that it keeps data private and secure. You need to trust that they're efficient. You need to trust that the systems are robust and resilient. They're not just going to sort of fall over. And federated learning is the core technology that actually, unlocks all of this. And, I know that talking to ARM, for instance, ARM view federated learning as a key technology to enabling a greater acceleration of sale of edge computing chips and devices, because it allows the user to actually utilize those devices.
Excellent. Well, you talked a lot about a tiny FL and ARM's belief that it is going to be crucial in edge. I was wondering what other trends and advancements do you kind of anticipate in the field of federated learning, and maybe its integration via IoT devices, or indeed the advancements in IoT that will make federated learning a lot more necessary?
Yeah, well, I think the overall trend is inevitably the temptation to kind of push the learning step onto increasingly resource-constrained devices, both in terms of compute and power constraint. That's clearly the case also because, like I say, there is this trend, I think, in IoT around battery-powered devices, so one sort of has to follow the other. I think it is an open question, though, as to what degree we need to go all the way down to the microcontroller for the learning step. We can leverage the heterogeneity of compute in IoT systems. Learning doesn't need to happen in the same place as inference, for instance. So I think that's not totally guaranteed. And talking to ARM, that their view is that really federated learning, from their perspective, enables better use of kind of sort of slightly higher resource devices for the learning side of things. So I think that this kind of push towards getting sort of learning down onto smaller and smaller devices, I think simply because kind of the macro trends out there are that the regulatory environment is going to change very quickly, and so data privacy for the consumer is going to be hugely important. The way that the geopolitics of the world are going, people have increasing degrees of cybersecurity concern, particularly in their critical infrastructure. So again, securing things to the device level becomes important. And then there's just the economics piece. Enterprise is now changing its behaviour. They've done their large-scale POCs and done the maths and realised that the economics of shifting everything to the cloud just doesn't work, and so they need to kind of leverage more of their near or far edge computation. So I think these are kind of, some of the key trends there, and that's going to result in us trying to sort of spread learning across sort of a spectrum of devices. But I think there's an open question about where the bottom end of that really exists at the moment. But like I say, that kind of tiny FL piece is still probably a couple of years away, really.
Okay, well, I think that's a good place to end it. It's been a fascinating, forward-looking podcast. So thanks for taking the time to speak with us today, Eric.
Absolutely. It's been my real pleasure. Thank you very much.
Remember to subscribe to IoT Unplugged wherever you get your podcasts. And don't forget to share with anyone you think would find it as interesting or as informative as you have. IoT Unplugged. Tune in to the Internet of